Okay, I think we are recording. So I'm gonna start up a whiteboard. Okay, so could everybody see the whiteboard? I would hope so. All right, awesome. So, data paths. So what is a data path? So, what you've been learning so far, and I think in the prerequisite for this class too, you're dealing with MIPS, assembly language, right? And each instruction that we have, each line is an instruction. Each instruction it does its own thing in the data path and like the circuit of the computer, that kind of thing. So what I mean by this, we'll start with a simple instruction. So for example, let's say we have an add instruction, right? And let's just have like, I don't know, two registers. Let's say this is S3, um, S1, S2. I think this is how you would write this. Okay. So this is an add instruction, right, in the MIPS language. And what this does is the first parameter here is the destination, and these first two registers, or the second two registers you see here, these are being added to each other. The value in here is being added with the value in here, and then that answer is going to be put in here. Okay? So when it comes to the data path for this instruction, right? Um, let's see, how do I say this? In general, like there's a lot of components to it to a data path, but think of it like this: some instructions use some components, while other instructions use different components, right? Not all components will be used at the same time. So when it comes to the add instruction, um, let's see. So maybe I'll make some more space over here. I'm gonna move down some more. Let's go over here. So let's just draw this box here. So all data paths, right? We're gonna have a PC. PC is short for program counter. It's basically what instruction we're on, okay? So we have this in the PC. It goes to this box here, called the instruction memory, or I'm just gonna write IM for short. And Georgios in the chat brought up a good point. So this add instruction, right, and like subtraction and things like that, they fall into this category of R type instructions or R format, right? And so before we continue with this data path, let's let's see how this add instruction would look like in, I guess it's like R type kind of format, like the different components of it. So of course with the R type, so okay, first of all, let me do this. Every instruction, this is very important. Every instruction is 32 bits. Okay? 32 bits. Okay? It's just depending if it's an R type, um, a J type or anything like that. The 32 bits, the bits they're just split up in different ways. So when it comes to an R type, the way that it's split up is that I believe the first 6 bits here, this is the what we call the opcode. Opcode. Let me type it. And for this class, this isn't really important when it comes to the opcode. This is just for the computer to know like what instruction it is. But 6 bits are dedicated for that. And then we have so we're gonna have 3 sections for each of the registers. So this is gonna be 5 bits. This is gonna be 5 bits. Yeah, this is gonna be 5 bits. Um, and these are going to be our registers here. And then we have 5 bits over here. I did an extra section. There should be 5 bits over here and 6 bits over here. But these, you don't need to worry about these either. Like these are here, but like you don't have to know what these are for like an exam or a test or something when it comes to the R type instructions. But in any case, we need to know how it's split up in order to build a data path. So yeah, going back to the picture we have here, program counter goes to instruction memory to fetch the instruction. The size of this is 32 bits. And then outside the instruction memory, and let me type this out just so we're all on the same page. Instruction memory like this. Um, and then now that little diagram I drew above, we're kind of going to use that over here. So this is 32 bits over here. So to be more specific, so going from like this PC to the IM, this 32, this corresponds to the address of the instruction. Okay. And then we put that address into the instruction memory to get the instruction itself, right? We were searching for it, we get the instruction. And now this instruction here is coming out of it. So this is the actual instruction. Okay. And so yes, we have the opcode, which is 6 bits. Um, and then we have the 3 registers, which are going to be 5 each. And when it comes to her exams, um, generally, I mean, you want to write the sizes for everything. Like you see how on the line I'm writing 32, and here you write, how many bits are dedicated to each section. And wait a minute, let me make sure I'm doing this right. Yeah, okay, this is fine. Oh yeah, and just so like let's say you get confused on an exam, it's a good way to check. Like, oh, did I put the right amount of bits for each section? You just add these because you know this has to add up to 32 because each instruction is 32 bits. And it does. This is 20, and then we have 2 6s, that's 12, so that's 32. Okay. Anyways, so after this, we're gonna have the register file. So it's gonna be like this. Um, let's call it register file.
Can I say something?
Oh yeah, yeah, go ahead.
If you cannot see what Anthony's writing right now, just try to scroll up the screen so you can see the whole picture. Yeah.
Yeah, and also if anybody's any questions, feel free to type it in the chat or raise your hand or unmute yourself, right? Um, but in any case, so we have the register file, right? So this is where basically like the registers are, you can think of it like that, where we're gonna direct all of the basically everything in this section that we just drew. So register file, we're gonna have read register one, and then we're gonna have a read. Wait a second. I think I'm doing this right.
Yeah.
Yeah, yeah. Okay.
You have the numbers 06555.
Mm-hmm.
Just right there. It depends which format you're working with, if it's R format or whatever. So there you have to replace them with the op, RS1, RS2, RD, and then when you draw the lines, you write the bits.
Yep. And so basically on this left side here of the register file, Where so it says read register one and read register two. So that's basically saying, and it's not really, I mean, it's good to know what this represents, but you don't need to know. But just for understanding, right? This is saying like which register we're dealing with here. So an example we had S3, S1, S2, right? S1 and S2 would be the what you would call it, the registers we want to work with. Because on the right side here, we're gonna have read data one and read data two, which is different than read register. With the read data, we get the data that's inside the register. With the register thing, we get the register itself. See what I mean? So this is the data that's in the register, which is what we want to work with. And is there something else here that I'm missing?
Uh,
I think this is,
the
yeah.
right data. There is a
The
right to the register and right data underneath that.
okay, okay. That's what I was unsure about. Okay, good. So you have the right data. Um, oh yes, yeah, yeah. We need that. We need that. Okay. So now, how do we connect the instruction? And let me just label this rectangle we did here. I'm gonna call it instruction. So we're all on the same page. All right, the instruction. We broke it down into the parts. So for this specific data path, we don't really care where the opcode goes or like the bottom two things like this sham t or the function. We don't really care about those. But what we do care about are the registers. So um let's see, how do I say this? Going back to going back to a little above where we first wrote the add instruction and then we wrote that little rectangle next to it. I'm gonna map out where each thing is going here. What do I mean by that? So let me draw this box again. Okay. So essentially, even so, this is our destination. Let me type that. The S3, the first register that we have here. So even though the destination and the instruction comes first, it's actually going to correspond to this last register thing over here. You see that? Let me make this a little neater. Let's do it like this. So that's different parts of it. Okay. And then we're gonna have, let me use a different color here. I use like blue. So then these two, the registers that we want to add together, they're gonna correspond to the first two things over here. And I mean, there's like no, there's notation for this. So, and if you want to like see it again in a different format, like I said, Georgios in the chat uh has the different formats instructions. So right now we're looking at the R format. This is the R type. So would be considered the RS. This is the RT and RD. Um, I'm not totally sure what I mean. R is for a register. I think the D, pretty sure D is for destination, but I'm not sure what the T and the S would be. Maybe source for something. I don't know, but that's what it is. And yes, so that's important to know for this data path. So going back to the data path now, right? Let's draw some arrows. Let's use this color. So we know that exactly. So we want to read this register, okay? Because we're adding these registers together, or what we're adding the data in the registers together and putting it in a new register. And then this register is going to be this is the target register, right? So we're going to put the sum in there. All right. So now read data one and read data two. So we so again it's add S3 S1, S2. So we take what's in S1, which is happening here. We take what's in S2, which is happening in here. Okay, we need to add them, right? How do we do that? We use an ALU. And an ALU is for these like computation stuff. This is a terrible ALU. Let me make that better. This, something like this. All right. Okay. And so each one is gonna go into the input here. So this is our ALU over here. Okay. Now we're gonna add them. Okay. And then out here is going to be the sum of what's inside the registers. Okay. And then let me think. Yeah, so that's it. So then we have the sum now, and we want to put that into the right data because basically, again, on this left side here, we're saying, okay, we're going to take this S3 register. We want to write into that register. What are we going to write into it? Over here, we're saying, okay, we're going to take the sum and put it here. So we're going to write into that. I'm going to put that into the register. And we're not fully done yet. I feel like there's something I'm missing here. Like I feel like this is too not easy,
Yeah.
but it's
So you need also the +4 for the next instruction. That
yeah,
the PC with the line of PC2 instruction memory.
exactly, exactly. And I was about to do that part, but then other than that, like everything else seems fine here, right? Because I feel like there was something or more on this side.
Yeah, just make sure when it reads the data 1 and 2, it's both 32, the 32 bytes.
Oh yeah, yeah. Let's label everything. Okay, so let's label everything here, and then we're gonna go back to the PC plus four. Like Giorgio said, that's a very good. You
Oh,
have to take that into account.
Anthony, that's 5, 5, and 5.
Oh, you're right. You're right. You're right. It's five. Exactly. So it's five, five. This is five. And then coming out of here, however, these are 32. This is going to be 32. This is 32. And the output, the sum is 32. Uh, and as a side note, when you have an ALU and you're adding these like two things together, they have to be the same size, right? Um, ooh, I can't. I do that. I'm trying to erase. There we go. I want to fix this over here. Okay, so this is 32. And that slash that I'm doing, that's to like denote size. If you want to say the size of it, you just put the number in like slash the line. At least that's what the professor does. Um, anything else that's important here? And yeah, and like a real data path, like if you wrote the full one, like this will go somewhere else, and then these two will go somewhere else, but we don't care about those right now. All right, and then now, so we need the next instruction. So these R type instructions, they don't affect what the next instruction would be. Like a jump, for example, a jump, we're saying, okay, if this is true, or we're just saying, okay, we're going to go to this instruction. Or a branch instruction, we're saying, okay, if this is true, if this is false, we're going to go here. R type doesn't do any of that. We just always go to the next one. So I'm going to make a little circle here, right? To like divert this line. So it's also going to the instruction memory, but at the same time, we want it to go somewhere else, this PC line. And then the next instruction by default is PC plus four. Um, so what I do, right, and I don't know if the professor mentioned it, but like we can have what's called an adder here. It's just an ALU, but all it does is add. You could just denote it by a square and a plus sign. I mean, an ALU also works with the other input four and just show that it's adding, whatever. But then it's going to come out of here, right? And this is going to represent PC plus four. This is what it's representing. But again, the size is still 32. have to make sure you show that. And then we just have it go back to the PC. And then the next instruction is ready to be executed. That this looks okay to me. Um, I mean, if anything, I'll label this as program counter too, so we know what it stands for, right? Instructions, here they are. Georgios, how does this look to you?
It looks correct. Make sure in the instruction memory it goes from PC to the address and it leaves from the read instruction. In the instruction memory, you need to write for the left line that it's the that goes to the address of it.
Like a read port.
Yeah, like you wrote the read the register one just right here where I am and one here.
Yeah, so would you mind doing that? Because I'm not entirely sure what would go there.
Yeah, so this this line here, it will enter the address. And this line here, it will find the address and then it will continue by reading the instruction. So just write read. Sorry for the and that will be the final of it.
Okay, and what does that say? In the instruction
So
on this
the
side?
PC will enter to find the address and then it will exit by reading the by starting to read the instruction of that address.
Hmm.
Just make sure you have it on your exam.
Yeah, exactly. Yeah. So like the register file, we show that this is read this, read that. Same thing with the instruction memory. Because we can't just have a line to a component and just leave it blank. Like there are ports. So we have to label the port. That's all that is. And yeah, so I think this is good for now. And we can move on to a different kind of instruction. I'd say that the R types are relatively simple when it comes to the other ones because the other ones they use more components or different ones and stuff. Um, okay, what should we do now? Let's do a branch instruction. I feel like branch is the trickiest of them all. I mean, once you know how to do it, you know how to do it, but you'll see. So a branch instruction, BQ branch if equal. And what does that mean? So we're gonna have two registers. We want to see if they're equal, right? So let's have the two registers. Let's call it S1. Let's call this one S2. Okay, if they're equal, um, we're gonna go to this address and we just call it label, but it could be anything. Just calling it label. And as you see, there's no dollar sign because this is not a register. This is an actual address. Okay, so now that we know what this means, right? Knowing what it means helps a lot, right? Because you may forget how to draw the data path, but if you know what it's trying to do, then it should be okay. You have better luck. So again, as always, oh yes, yes. By the way, I moved to the right of where we were writing at just now. My fault. Um, okay, and again, this branch instruction. So, all right, so let's do this. So again, as always, we need a program counter, right? Because we have an instruction. This is an address. That's 32 bits. Okay. Oh, and speaking of bits and stuff, I don't know if it's bits or if it's bytes, Georgia. So you know the difference if it's bits or bytes?
It's bits.
Bits. Okay. 32 bytes would be crazy. Oh, that's really big. Oh yeah. Um, so anyways, this is the instruction memory. Okay. And then like before we need to label the port. So this is the, I guess, read address over here. Let me move this up. Oh, let's do it like this. Okay. And then we're gonna have what will go on the right side over here, Georgios?
Read instruction.
Read instruction. Okay. So yeah, we have read
You
instruction. I'm just gonna write this for short.
it's the same.
Weapon?
You can just write instruction and address. It's the same. Like don't
Oh,
write the
they don't even put the read part.
yeah,
Okay.
it's fine.
Okay, okay. So yeah, so we have that now, and then we're gonna have now the instructions. So this is where things start to change, right? Because as always, these first two are always gonna be the same with the PC and IM. This is, I can do this better. Let me change this. So now, before we continue, we have to know what kind of instruction a branch is, right? So a branch is, was it, is that L or I? I don't even know what that is. So what are the types? This is how it looks. So with the branch instruction, again, we have, and I'm writing above the data path picture we're just working with. Let me use a different color. Everything here is the same thing. Let me change this and let me use a thicker thing. Okay, so I'm gonna write above the instruction I typed out or draw above it. I'm drawing this rectangle right now. Okay, so all instructions, the first 6 bits are gonna be the opcode, no matter what it is. Okay, and everything is also the whole thing is 32. So always keep that in mind. 32, 32, 32, 32. So our opcode. Okay. So now, as you see, we have two registers. Um, I think we just call them like this, RS and RT, right? Um, or you just, I'm not sure exactly what they're called or what it means, but we just have the two registers here, and they're 5 each, always. And then this is going to be, because you see, now we have the label part, which is, it's an address. And I think the term is immediate, the immediate, um, or in any case, we could just call it IMM. I think it's short for immediate. Am I right, Georgios?
Yeah.
Okay. And this is going to be 16 bits. And you know what's funny? I wasn't fully sure, or let's say you're not fully sure how big this is. Again, we know it's 32. The opcode's always 6, registers are always 5, right? So this will be 16 we have here. So then this has to be 16 to add up to 32. In any case, that's how it's broken up. So let's do that here. Going back to the data path we were just drawing now. So this is 6, this is 5, this is 5, and this is 16. Bam. All right. And as always, we have the register file over here. Also, yeah, so if you check the chat too, Joe just attached something that relates to the branch instruction. So if you want, you can check that out as well. But in any case, once you have the register file, I mean, all the register files are the same. We just have the read and the write ports. So one, just do like this, read register two, and then we're gonna have the write register like this. Just do it like this. All right, so we're just gonna change all the registers to data. Okay, bam. So, um, yeah. So we're gonna just read the first two registers. Okay, we're gonna take them here, and then we want the data that's in it, and we want to see if they're equal, right? So to see if they're equal to each other, what we do is we have an ALU still, right? Because we're doing a computation. So like this, okay, and um, so and yeah, let's label the lines. So going back, so this instruction over here, so this is going to be 32. These are going to be 5, 5. Out here is going to be 32. This is going to be 32. But this over here, I'm quite sure this is not 32 now. This is just going to be 1. This is 1 bit coming out of here. Okay? Why is it 1 bit and not 32? It's because we're just seeing if they're equal to each other. So if they're equal, it will spit out a 1. If they're not equal, it spit out a 0. Okay? And it's important too that it's 1 bit coming out of here because this is going to go into an AND gate. What AND gate? We're going to get to that in a second. So now let's going backwards. Let's focus on this immediate address over here. um, Georgios, I'm forgetting. Do we sign extended first or do we shift left?
So if we take it from the beginning, first of all, the what the
Uh,
ALU does, it's subtraction of RS and RT. And if it's 0, yes, the bit will be 1. But you can continue as you go and then you can add the shift left.
oh, like just continue with this? Okay.
Yeah, continue as you go and we can add the things later.
All
Because
right,
there's
no problem.
no right order of going, like depends.
Okay. Yeah, because I know when I do data paths, like I would do this, what we just did over here, and then I go back, and then like I will have everything neat. But yeah, let's keep going with this. So in any case, the output here is going to be 1 bit. Where's that going to go? It'll go into an AND gate, and let me think. I'm trying to figure out what direction. Let's go down. Let's make this go down. Let's go down a little bit. Okay. And again, it doesn't matter if you go up, down, left, right with the data path, as long as it makes sense and everything's connected.
I think it's better if you go up, but it's
Up.
how you are feeling comfortable with. Because down, you will add something else later.
All right. Let's go up then. Let's go up. All right. So we're gonna bring this up, and we're gonna have an AND gate over here. Okay. So just looks like a dome. Okay. So why do we have an AND gate, right? Um. So we're gonna branch. So the branch, right? We have to have a branch instruction, and once we have the branch instruction, the numbers have to be equal. So this is what this is telling us. So this line is saying, okay, the the registers were equal. Okay, this line is saying we have a branch instruction. And let me Let me just type this out here. It's a multiplexer?
Yeah, because you check if it's 0 or 1. And if it's 1, you continue with the next instruction. Otherwise, if it's 0,
Um,
you no.
wait a second. Because no. I think it is an AND gate, and then we have a multiplexer. Because because after this AND gate, we're gonna feed the output of this AND gate into a multiplexer, and then the multiplexer we're gonna have the PC plus four, or we'll have the target address. You see what I mean?
Uh, I
Um,
see
and you know
what.
what? Here, I'm gonna look at the just sort of the same page. I mean, you could be correct too. I'm gonna look at what Joe had attached, and we could just use that as a reference. Let's just see um what you call it. So this is what's in this PDF over here because we don't want to be wrong. Um, this is just the actual, not the data path, but the actual I see what this is, like how each thing is broken down. Okay, the data path. In any case, I'm gonna look up the branch data path then.
Oh
Let's make
yeah,
sure.
I can find there's a document like a PDF that has basically the entire thing, and then you follow the path. So I can find that for you too if you want.
Oh yeah, that would be great. And you can put that in the chat so we can all see it. Um, but this is the way that I've done it, and because we need an AND gate, because even though well, actually, it depends, because sometimes on an exam she'll be like, assume branch condition satisfied, and so in that case we wouldn't need this, but for completeness, I'm still gonna add this here. So the other line coming into this AND gate would be um a branch. So basically, we're saying so like in a different part of the data path, there is this, I think you call it the control, right? Where that's where the opcode goes. So the opcode will go there, and basically it will tell the whole system like what instruction we're working with. And in that case, whatever happens, so this line is also 1 bit, but then this will be a one. Like the output here will be a one if we have a branch instruction. Okay. And if we don't have branch, then this will be a zero. Because in order to branch, we have to have a branch instruction and they have to be equal at the same time. Okay. Um, and then yeah, so Georges was talking about a multiplexer. So that comes into play over here, where we have a multiplexer over here. And again, I forget how she asks things on an exam, but based on like if she says branch condition satisfied or this and that, you could just probably skip the AND gate step and go straight to the multiplexer because we know there's a branch. So we don't need to have this AND gate to toggle things or not. Let me make this a little better. Let me use a different color now. Let's do this. So let's have this multiplexer here. And then let's do it like this. So this is going to be one, and let's have it zero. And again, what a multiplexer does, and this line is one. That's a 1 bit. So what a multiplexer does again is whatever the input here is. So if this is a zero, we pick the zero thing. If it's a one, we pick the one thing, or whatever goes into one. So we have inputs for the zero and one, and it toggles it and it picks this. Okay, Joe just attached a PDF with data paths. Let's check that out. Make sure we're all on the same page here. Yes, exactly. Okay. Cool. Um, How do I do this? I'm gonna put this into the whiteboard. So I'm gonna take a screenshot of this. Um, Go here, here, here. Um, Hold on. Okay, so I just put this picture in here. I'm gonna drag the picture underneath the PC that we drew. So it's kind of out of the way, but we can still see it. And I think that's big enough for people to see. If you need to see more detail, you can zoom in. Um, but yeah, so what we're focused on is let's use this red color here. So look, this is where we are. This ALU part. Okay. So you see where it says zero? I'm drawing on the ALU right now, the picture of the data path, the picture I put in here. So this zero thing I'm circling. Okay, so this is check for zero, okay? And this is 1 bit long. It goes into this AND gate over here, okay? And you see the other part of the AND gate is this branch control line, right? If we have a branch instruction from the control component, and right, you see the top 4 bits here, the opcode goes here. But we don't need to draw all of this, the opcode and coming here and right, we're not focused on this. But you can literally, I'm pretty sure, like if you were to draw the AND gate, you just have this line coming out, just call it branch, and you could just leave it just coming out because we know where it's coming from. But what's important is this zero comes to this AND gate, and this AND gate is the input to this multiplexer here. Um, yeah, so that's what we're drawing over here. But what I was saying was that on an exam, she may be like, assume the condition is satisfied, right? So what that means is that we know, or yeah, like you can say that. So we know that this we know that one this will be selected here because if the branch condition is satisfied, that means that we have a branch. So this will be one. It we check for zero, like they're equal to each other. So this is one. So then the output of this will be one in this AND gate, and then we'll pick this out input then. So this will come out. So the target address. So basically, we will branch. So in that case, if the branch condition is satisfied, I think we could just get rid of this whole AND gate and just go. Not even like I think skip the multiplexer too, and then we'll just have this result like the address that we want to go to. We calculate it, and then we just send this all the way back to the PC like that. Like we don't even need the multiplexer. But for completeness, let's just draw the whole thing just so we understand what's happening, right? And it'll make more sense. Um, so yeah, going back to the actual picture or the thing we're drawing. Um, so that's pretty much it for, or there's one more thing. And then we're gonna go way back to the 16 immediate section of the thing and how to calculate the target address, the TA. So this branch is, so I'm gonna just drag this up here. And we need a PC plus 4, okay? Um, so again, by the PC, I'm just going to divert it, making a dot here and have the dot also go up, 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 up. And this is a little long. Oh, I need to get rid of the whole thing. Let's just go here. Okay. So we have this PC. What am I doing? I don't want to do that. This is straight line. We have this adder here. We're just gonna add the PC plus 4, right? So we have 4 over here. And then the output is just gonna go here. Okay. So, and again, all this is 32. This is 32. Okay. So the idea here is that that's multiplexer. So the zero, so basically we're either going to go to PC plus 4 or we're going to go to this new address that we're about to calculate. Okay, so that's what is going to go into this one slot here, the new address. How do we do that? I'm going to refer to the picture one more time. And yeah, you can just go back and forth between this photograph here, this picture, and what we're drawing. And as you can see, yeah, like I was saying before, like you don't have to draw the entire data path, just the parts that we're working with. Like you have this component over here that I'm circling right now in the picture, right? We're not going to use any of this. This is the memory, right? We don't deal with that. There's other things we don't deal with. But anyways, what are we working with here? So it looks like, as I was saying before, do we sign extended or shift left first? And it looks like here we have to sign extend. Yeah, we sign extend and then we shift left. Okay. Yes, let's do that. So, yeah, I think I should have went down because whenever I do the branch too, like the lines like overlap with each, well, they're overlapping in the picture. It's okay. So, going back to the drawing, I'm drawing now from the 16. We have it over in the instruction part, and I'm going to use green, using a different color now. And we're going to go this way. And first thing we're going to do is we're going to do something called a sign extend. So we can make a little circle here. You can write sign extend, you can write SE for short. Okay. Why do we sign extend? What is sign extend? Extend. Okay. We know that addresses, instructions, everything is 32, 32, 32. This is 16. We want it to be 32. So we're going to extend it. Okay. So this should be 16, but after the sign extend, we're going to make it 32 so we can work with it. Okay. Um, yeah, I'm gonna do some crossing stuff, but that is okay because we have to cross over our wires. Let's go up. Oh, yes, yes. And what JoJo's is saying in the chat, on the exam, you may have a picture of the entire data path, like all the components together. And based on the instruction that she asks you to draw, you just have to understand what's going on and draw a subset of what you see here. Like right now, we're doing a subset of all the components here and the connections. And yeah, so
So she will ask you to explain in detail what's going on. So every time you draw something, just make sure to write as well what you're doing.
exactly. Okay. So after we sign extended, we're going to do something called the shift left or shift left two. And you can write shift left two, or you can also write SL um L or SL2, whatever, shift left logical. I'm gonna write SL2, like shift left two. All right. Let me rewrite this. Should be an S. That's an S. It looks like a five. I'm gonna try that one more time. Or better yet, I have an idea. I'm just gonna type it. SL2. Okay. Bam. So we're not done yet with finding out the target address. So we can't just connect it here, okay, and be like, okay, we go here if we branch. We have to calculate the target address properly, we have to add it to the PC plus 4. So what do I mean by that? And you can always refer back to the diagram below. So with this PC plus 4 we have here, and let me illustrate that this is PC plus 4. Not this is not the size is not PC plus 4, but this is what the line represents, PC plus 4, right? Just for clarity's sake. So we're going now to take part of it. I'm going to make a little circle, and we're going to divert it down this way. Okay. So part of it is still going this way, but we also want part of it here because we want to do some math with it. So we're gonna take it. We're gonna add this to the immediate after we shifted it left. So the ALU here, we're gonna have this, and then the shift left. We're gonna put it in here after we shift left. And again, of course, this is 32. The size didn't change. Ooh, 32. This here is 32. And the output here is 32. Okay. And the output here is 32. 32, 32, 32. Okay. Um, and yeah, so this is also an ALU. So what's happening here? What did I just do? So to say it one more time, right? With calculating the target address, you're gonna see it a lot in class probably, and the other TA. Okay, the TA. You're gonna have to find the TA in the load, the store, this, the jump. But when it comes to the branch, find the target address, you take the immediate, okay, you sign extend it, you sign extend it. After you sign extend it, you shift left two, shift left two, and then you add it with the PC plus 4. Or you just put in the ALU with the PC plus 4. And then that becomes the one input in our multiplexer. And then the other one is the 0 input PC plus 4 here. And then one last thing. Um, we're gonna connect it all back to the PC. We have to go all the way up, all the way around, and then we're gonna go back to the PC because that is the next instruction, the address of the next instruction. Um, and so what I was saying before that if she says branch condition satisfied, um, branch condition satisfied, then you can just, I think you just omit the AND gate over here, omit the multiplexer, and just have this like we would just go from here. We have to still have the PC plus 4 line and add it together and stuff, but we could just go from here straight there. We don't need this multiplexer and AND gate. From what I'm gathering. But yeah. Um, anything else? Georgios, would you say anything else about this?
I think, yeah, it looks good.
Okay. Um, all right.
So
So
you did an I format right now. Do you want to do the other one as well?
the jump.
No, never mind.
Yeah, so I mean the J format is the jump and like it's just by I think J is just for jump. That's a special case. But what I wanted to do too is load and store. Well, not both. I don't think you have time. Well, we have time, but load and store are pretty similar, but they're different from the other ones. Because about the target address, the TA. Let's do let's do a store. And then we could do a jump. Or like is there one you guys want to do first? A data path? Anybody want to type in chat or like, because I can do either one. All right. Either one is cool. All right. Okay, we go overload then. No problem. So I'm going to move. Actually, no, this is pretty funny. I'm looking at the first. So we did add up, and this work is so much larger than the other work. It's like, wow, it's like tiny. All right, I'm gonna move to the right of what we were working at, a little over, and so now we're gonna do the load. So let's do load. So LW is for load word. Okay, word. Just think of it like a piece of data. Um, load. Wait, I'm forgetting the format. Let's say S1, and then we have this, and then like an offset, and then we have another register S2, something like this, right? Right, Georgios? Or- Yeah, it's like a fractal. Yeah,
Yeah.
like this, right? Okay,
Yes.
okay. So what does this mean, right? This means so load word loading is we take something from the main memory and we load it. We put it into the register. Okay, so it's from memory to register. That's what loading is. Um, so basically, we want to go to the memory and put something in this register here. All right. And where do we go into the memory? This is going to tell us the target address in the memory to get that. All right. So how do we start off again? Always, always PC. Okay. Like if you forget the entire data path, like if you don't know anything, at least just do this. All right. You got the IM. Okay. This is 32, as always. Okay, we have the address port. I'm just gonna type it. We have the address port, and then over here we're gonna have the instruction port. Let's try to add that for short. Let's do it like this. Okay. All right. Anyways, bam. So now instruction. We have the instruction now. We're gonna break it up into its components. So again, as always, every single instruction, the first 6 bits are the opcode, the operation code. I think that's what op stands for. Um, and then bam. So now we have the rest. So when it comes to load, so right now I'm gonna start writing above the instruction that we're using as an example. So like how does the format of this look? So again, we have the 6 bits for the opcode, and then the S1. So that's the destination. That's where I'm just gonna call it like I don't know, like RS, RT. I don't know, I'm just gonna call it RS. I don't know what to call it. Um or like RS, whatever it is. And then now it's what is going here? What going on over here? Um Georgios, you remember exactly how this is broken down?
What do you mean?
For the load word, like how how it's like portioned up.
So it's RS is 5, RT is 5, so it's 6, 5, and 16.
Oh, okay, we just have okay.
Yeah.
Um, wait a second.
So as one is
Oh,
for RT.
Wait, yeah, so it's 655
and
and
16.
then 16, right?
Yeah.
So same thing as the branch. Okay, okay.
Yeah, it's
Got you.
like format.
Yes. Okay. Okay, cool, cool, cool. So yeah, so it's the same format as the branch, but we're gonna do different things with these things over here. And so what does each component here mean? This eight here, it's not like it's eight times S2. This is this is what we call like an offset. The eight is the offset. All right. Um all right, let's just do the register file. Or actually, can I just copy the register file that we had before? I think I can. Just drag it over here. I don't feel like doing it again. Okay, let's do it like this. Okay, bam. And then I'm just gonna get rid of this. Bam. All right. So, um, so I'm not sure if the offset is in bytes. Georgius, what do you have to say about that? I'm not sure.
I mean, 16 bits looks okay, but you mean D8 if it's a byte or bits? So I think 8 should be bytes. Let me make sure before I give the final answer.
Okay. And I'm again copying the diagram. I'm putting it underneath the drawing we're doing right now. I'm gonna erase these marks. So yeah, we could just cross-reference what we're doing with this because I'm a little unsure as to how we're going to connect everything. So I'm just making sure. Okay.
So 8 is in bytes.
What's going on here? Um, oh, I see. I see. Yes. Yes. And then to calculate the target address, we go there. Yes. Okay. Okay. So this is what's going to happen here. So going back to the instruction, like the actual text that we have here with the load word S1, S2, that thing, I'm going to make some arrows to show what is going where. So this S2, if I if I'm looking at this correctly, this is going to correspond to here. Yes, and then this S1 will correspond to this over here. This second register over here. Why is that? I mean, again, so this S1 is the destination. Like we want to put stuff into here. Okay. So in this case, so if you look at the diagram in this section, there's like a multiplexer over here, but I don't think it's necessary to draw that um for this, like for an exam or something. If you have to draw this, I don't think you need to draw the multiplexer. Um, so I'm gonna omit it for now. I'm gonna omit it for now. If anything, we can come back and I could just add it and draw it in and show how to connect it, but it may just complicate things. So this is gonna go here, and then this is gonna go here. The first register is gonna be red, and this is gonna help us compute the target address of the TA. This is 32. This is 5. This is 5. And now we have our immediate.
So again, we're gonna sign extend it. Or yeah, we sign extended it, correct? Yes. Okay. And let me just make sure. Yes. Okay. So we're gonna sign extended. And we should always want to sign extended because we want to, if we're like gonna do any math with this or something, we want it to be 32 because everything else is 32. And we gotta do things, we can only compute things if they're the same size. So this is 32. So now what? So going back to this register file, let me label it. Okay. We're going to um I'm gonna have an ALU over here. So this read data, you're gonna be connected to this ALU like this. This could be drawn a little better. But you get the idea. It's an ALU. And so what's gonna happen here? And right now there's another multiplexer that's supposed to like be over here. I'm just unbending the multiplexers for now and just showing you how everything should be connected. Um so yeah, this is our ALU over here. And what's happening is that we're taking the immediate, we're sign extending it, and then we're adding it to, and this is 32 as well. That's why we sign extended, because this is going to be 32, and we need to add it with another 32. So this is going to be our TA, our target address is going to come out of here. Okay. And so now we're going to use a component that we haven't touched before, which is the main memory. Okay, because that's where we're loading the word from. We're loading it from the memory
Before
onto
you,
the registers.
after you sign extend and you go directly to ALU, there is a multiplexer there.
Yeah, yeah. So that's what I mentioned. And there's a multiplexer over here too, multiplexer here.
Yeah.
I just omitted it for now
Okay.
because I'm not sure what will be demanded on the exam. Um, but if anything, I'll come back to this part, and then we can put in the multiplexer. Okay, so let's go back. The target address. So this is our main memory. Okay. A lot of times just MM for short, or just memory, whatever. And um what do you call this port? Just a read, just a read address. Because again, the TA, the A is for address. So we have an address here. So we're reading it. Um, you could probably just write address or read address. So get that idea across. And we have the address now, and then the output here, we want the value in there. So I think this would just be a read data. And I could just double check the diagram we have here. Yeah, exactly. Read data. Okay. And the diagram also just has address here, so I'm going to be consistent. I'm just going to write address. And yeah, so we read the data, and then we want to put it into the register that we want to write into. So you just pick a line, we just go here, and yeah. Um, but again, we're not done because we need the PC plus 4. That goes for pretty much everything. I'm going to drag the diagram a little lower so I have some space and make this line over here. We're going to go down and let's just do this same setup. You could just set up this adder over here or ALU, whatever you want to call it. We're always just going to add 4 to it. And then we're going to bring it all the way back here. Now we're good. And again, this is also 32. This target address is 32. The data here is 32. And again, like another way to figure it, like what the size is, if you don't know what the size is, like if it's not otherwise stated or if it's not obvious it's something else, it's probably just 32, right? Everything's 32. Um, but yeah, so like Giorgio said, multiplexers. Where would they go here? Oh, and also I forgot to add something. Not like it matters too much, but there's another port here called write data, but we're not using it, so that's why I omitted it. But if you were to use like this, there is just this port here as well. So I guess you just write all these ports, but for this case, we just care about the read data. We're not writing into the memory. Store word, the SW, we would do something about this. But here we don't have to. Um so multiplexers. Um I'm going to start with the multiplexer that we need between the register file and the ALU. So, um, I mean, and it's a pretty like simple multiplexer here, um, where yeah, because I'm just double checking it with the diagram, but it's just we're just toggling between read data one and the immediate. So let's do it in a different color. Let's do this in let's go back to black. Okay, I'm not sure what this is over here, but over here, let's have this multiplexer. Let me get rid of this lines. Let's like get rid of this over here. I'm gonna have a multiplexer. Just do it like this. Uh, let's say this is one. Let's call this the zero input over here. So essentially, because like with the multiplex, with the non-multiplexer, with the ALU over here, it's usually like we're adding the first two read datas, but sometimes we don't. It depends on the instruction. So we're gonna have this toggle switch over here like this, and then what's in here is gonna tell us this is the also coming from the control thing, right? Pretty sure this is called ALU source, SRC. Just gonna double check, because we also have another uh like control thing for load. So you see, if you go to the diagram, right? I'm drawing on it right now. We have this memory read thing, and we have this memory to register. So memory to register is load. Memory read is memory to register. Yeah, memory to register is load, and memory read is no, sorry, memory write. Memory write is store. Also, it's confused. Memory write is store. The corresponds to store. Um, and for the load, it would activate this memory to register and memory read because we need to read the memory too. But storage is memory write because we're not reading any memories, we're just writing into it. Anyways, let's go back here. So another multiplexer we can add is, I think, a more relevant one would be after the main memory over here, in which we would use we would use the multiplexers that are unique to the load instruction. So let me just make sure I'm looking at this correctly. Okay. Okay. And then after this, we can hop over to the jump. or I need to charge my computer. So I'm gonna take a moment to do that and then or like plug it in and then we'll get to the another instruction. But in any case, I'm gonna erase this here. So another multiplexer, I'm by the main memory part of where we're drawing. I'm going to add this multiplexer like this. And then let's say this is our one input. Let's call this 0. Okay. And let's have the select line here. Okay, and let's have the output just go back here. Yeah, no problem. So what is happening here? So when we have a load, right? Load is bringing something from the memory to the register. So this line here, this is the mem to reg, like this. Okay. And so it's either like, and you see how this line, the output of this multiplexer is going into the right data. So um the other input for this multiplexer would be we would divert this target address here and we would go to the 0 input over here like that. So essentially, if we have a load, then we compute the target address, and then this will be a 1. So this size here is 1, but then like we would select this one over here. Okay. And then we would do that thing. And then yeah. And then we have another multiplexer over here, but I feel like we probably don't. I don't think you need to draw this one. This is kind of unrelated, I feel like. Um, but we could still do it. Let me see what this is about. Yeah, I'll still do this multiplexer for completeness, and then we can jump over to a different one. Um, okay. So the space here, yeah, I'm gonna erase this over here. So what is this multiplexer for? So basically, sometimes this register can like go over here. Yeah, yeah. Because with the branch, right? A branch has the same structure, the 65516 structure, but with the branch, we go here. With the load, we go here. So the multiplexer is telling us like this helps toggle which register or which port this register would go to, right? So um how did it work in the diagram? So in the diagram, we have, oh, okay, I see. All right. So in the diagram, right? So basically, we're saying like this line would always go here, but we can also divert it, making a little dot here, and then we can go down this way and have the option of it going into the right register, like this. So this multiplexer here, the output is going here. Okay, let's say this is a 1. And the other input of this multiplexer, I believe, is this over here. Let's call this the 0 input. Let me just make sure the work is correct. Or no, no, sorry. It wouldn't be this one. Like, how do I describe this? And I think this is also why this multiplexer just probably won't be demanded of you because so the computer doesn't know how like each thing is broken up. Like, sure, it's 32 bits, but if you look at the diagram, right, it says like instruction and then brackets and then numbers. Those numbers tell you the bits of the instruction and where those specific bits are being sent to. So here, the last 16 bits are the immediate, but the last 16 bits, there could be it doesn't know what instruction, like how it's broken down. Like we could also have this 5 here. In any case, it's going to like this whole thing is like one thing is all 16, but it's going to send like the first 5 bits of this 16 to here too, because it could also be another register. Like with the add, for example, the add instruction, we had the 6555, the 655, yeah, 3 5s, and then we had other stuff over here. But in any case, it'll be something like this, where this will get sent to here, this file gets sent here, and then we have this the select line here. I think this is registered destination, like reg dst, right? And again, everything's in a diagram. You could just look back and forth to compare. I think it's a good idea to save the diagram for yourself, right? But yeah, and I feel like it's confusing showing it this way because it's not like we have 3 sections of 5 and then a 16. It's more like the 5 is within this 16 over here. So let me emphasize that, because this looks incorrect if we do it like this. So I'm going to write, like, make it big. I'm going to say that all of this is 16, including this. And then we like those 5 bits will go over there. And again, so if we have the load register destination DST, that's going to be a 1. So if it's a 1, then this line will be picked, and then this line will go here into the right register like we had before. But yeah, so that's all the multiplexers we're going to need for this one. And yeah, so we can move on now to the jump data path. If you have any questions, we can like go over this again, or some parts of this, or a part of another one that we did.
Actually, if we are done with this data path, should we continue with something else? Because I think the jump, you guys have it on your notebooks.
Oh yeah, like if there's another thing you guys want to do, like feel free to say it in chat, or unmute yourself.
Yeah, because we only
Anything you're
have
unsure
30
about.
minutes left. So if you guys want to see something else, let us know so we can go over it right now. So
Oh
in your
yeah.
exam, you need to know about some of the multiplexers. Okay, can we see that?
Made a table to analyze
Yep.
opcode.
What table is that?
I'm not sure if she shared it. I can see if I can find it. I'll be back because it's opcode is 6 bits, but I'm not sure exactly how to read that because there's also the ALU opcode, which is 2 bits. And I think it might be like, you know how 5 is part of the 16 here? It
Yeah.
might be that 2 is part of those 6, but it's a little bit unclear. So I'm gonna see if she had shared that, and then I can share it in the chat too.
Okay, sure. And yeah, and if anybody else wants to go over another topic, or like they're unsure, because it's your exam, make sure you do well. So now's the time. And while you guys figure that out, I'm gonna plug in my laptop, so I'll be back.
So what else you have for the exam? You will have to draw the branch condition satisfied or not satisfied and the load. That's part of your exam. Or we can go into MIPS assembly code for the pipeline implementation or the single cycle. We can go over jump, but we've already covered most of it, and I know that jump it's in your notebooks. Also, you need to know a couple of the multiplexers. I can, if you want me, start over the condition branch condition satisfier load.
Yeah, so this one, Lecture 16, has the ALU control unit, and that's the table that has all these different instructions for ALU operation and then the function for 6 bits. Um, and I guess that's not, maybe I confused that. Maybe that's not like the operation code, like the opcode Anthony was talking about earlier. I just want to make sure I understand how to read this properly.
So it looks like she's giving you. So yeah, you kind of have to know that table, the outputs of the control unit, but not the, like, where do you use the register destination, the reg write, the ALU source. You need to know the first table from what I know. And it looks like the answer is it's down, like it's the one that you are saying, Joe. But what do you mean, like the 6-bit operation and that?
Okay, wait a second. So I think I see. So the outputs of the control unit, this table at the first page is like left empty. And
Let me see if I can connect my
hmm,
iPad and I can show you the example.
okay. So the second table, our format, everything's set to 0. If everything is set to 0, then it's just going to know to do an R format to analyze the rest of the bits, right? Because bits 26 through 31 are going to be the opcode, right? That's 26, 27, 28, 29, 30, 30, yeah. And then bits 25 to 0 are going to be how you analyze. That's going to be based on if you know it's R format or load or store or anything like that, right?
Okay, from what I have on my notes from the when I took it, the table it's not the same as I see it in my notes, so I can give you the table as well. Because you don't have to know the off, you just need to know the first table there.
Okay. Yeah, sure. If you can share your notes too, that would be helpful.
Yeah, let me 1 second.
Yeah, and I'm looking at what you had attached with the opcodes.
Do you,
Um,
Anthony, want me to share my screen?
if you share your screen, we're gonna have to close the whiteboard, and then
Yeah, it's fine. I will write on my iPad.
uh,
So we are gonna close the whiteboard so I can share my screen. Does anyone want to copy anything from the whiteboard?
yeah, you said you're gonna share your screen.
Yeah, yeah, yeah.
Okay, yeah. So Georgie's gonna share his screen. So by doing that, the whiteboard will be cleared. So if you guys want to take any screenshots or if there's anything, any last minute like clarification you guys want with what we drew, like that, feel free. I'll give you guys a minute. Okay, I will stop or close the whiteboard now. Um, oh, I see. All right. All right, go ahead.
Yeah. So do you see my iPad now? Yeah. Let me see if I can quickly the table.
Yeah, I can see it.
Yep. 1 second. Okay, so I'm gonna draw the table instead of. So we have the R format. Load, store, branch, and jump. So in your exam, she will ask one of these. Where do you use one of these multiplexers? Jump, branch, rec, right, mem, right, and mem, read. So the register destination, for example, it's being used on the R format, not on the load. Obviously, not store, not branch, not jump. For the memory to register, it's 0. It's not using the R format, but it's only using the load format. Because when we load, we go from the memory to the register. We load. So it's not gonna be store, branch, or jump. The ELU source, it's being used in the load and the store, and the rest are 0 or X. You don't need to remember the table, like the whole table, just remember where the multiplexers are being used. So the jump, it's obviously being used in the jump. The branch is used in the branch. The register, right? So when we write something to a register, we are using it to the R format to the load, and the rest are 0 because we don't write when we store. And memory write is 0, 0. It's being used in the store because we are writing on it. And memory read is used in the load. So remember where each one of it is used. And I can show you one of the examples that she might give it in the exam. She might not. So we are going over the register destination. So if I'm using the register destination, I'm using a multiplexer with 0 and 1. So I have a register test coming in. So the 1 will come from the position 15 to 11. And the 0 will be from 20 to 16. And I'm writing it like that because if I have, like, for the R format, register, yeah, for the R format, when I draw it like that, I have the 6 bits here, 5, 5, 5, 1, 2, 3, I want another one, and 6. Here is the opcode, ERS, RS1, RS2, RD, and the function. So basically what I'm gonna write now, it's from the table, it's from the data path that it's gonna be given on you. So you see the 31 to 26. So it's like how from which position of the bits you're taking that instruction. So this is 20, 16, and so on. Like this space is 5 bits. So it's gonna be 11 because we have 11, 12, 13, 14, and 16, which is like bits. 5, I don't have 20, it's fine. So that's why you are writing it in this way, 20 to 16. That comes from the register 2. And the 15 to 11, that comes from this one.
Oh, thank
So
you very much. Because you can kind of see once the OP code tells it how to view these, then that's when the multiplexer decides to take either these bits or those bits,
yeah,
depending on. Okay, thank you. That's interesting.
here is the R format. And this one is from the load word. And then we write rec. So you basically need to know how to do this for every single one of them here. To be honest, I see that you probably have the ELU source and the memory to register on the notes. I'm pretty sure because I have them in my notes, so she probably went over them. So we can move on with me showing you the branch condition satisfied and not satisfied, because you will definitely have it in your exams. So give me 1 second. And again, this part here comes from the data part that it will be given in your exams. So for the branch condition satisfied, we first needs to check for 0. Branch condition satisfied. So as Anthony said earlier, we are using the AND gate. Here is a branch. Oh no, I have my two values coming in. So this part here is will be check branch for 0. So if I, for example, and because it's satisfied, we want to have 1, 1, and my output will be 1. So if my output here is 1, I'm using the TA branch. If it's 0, I have to jump. But first, I need to use the PC+4. So from this part here and this part here, when I have an N, 1 as an input, I move on with my TA branch. And again, I have another multiplexer there. And this multiplexer is for the jump part. But I don't want the jump. I want the branch condition satisfied. So what my input should be, it should be 0. So when my input here is 0, I will move on with my TA branch. If it's 1, I need to do the TA jump. And then I have my final, which is PC. If it was condition not satisfied, you can go with 0 or 1 here, but 1 should definitely be 0. And then if it's 0, I have this. Actually, let me not write on top of them. So it can be 0. So I will get a 0. And those two have to continue by going further. Like you change places of these two, I think. So yeah, but probably it's gonna be condition satisfied, so you don't have to worry about that. Or the other one that the exercise will ask you for, it's to do that for the load. So when I load, I still want to check for 0. So I still have 0 and 1, PC plus 4, and the TA branch here. It's again check for 0. So my one line should definitely be 0. And the other one, we don't really care because all we want is 0 here. And because we are loading, we are going with the line of PC plus 4. Because as you see, the input is 0. So if the input is 0, we are using this line here. Then I have another one multiplexer here. Again, it's my jump. My jump will be 0 in order to continue with this instruction. And the 1 will be jump. And my output should be PC plus 4. And I'm ending up with my PC. And at the same time, you don't only have to draw it, you need to explain it as you do it. If you want me to go over it again, let me know. If you have any questions.
So what you're saying is like if a question asks an exam for this, you just draw this whole diagram and explain what it does. And
Yeah.
okay.
So first you need to check for 0. So the steps is here. My input should be 0 for the load. And then because my input is 0 for my multiplexer, we'll go with the line of PC plus 4. It won't go with, explain that it won't use the TA branch because my input is not 0, it's not 1, it's 0. And then it will go through with the PC plus 4. And then I need to check for jump instruction, but because my jump instruction is 0, it will go through with the PC plus 4, and it will end up to PC. We didn't use the TA jump because the input here was 0 and not 1.
Thank you. That's a lot more clear now.
Yeah, and here at the same time, we need to compare we need to use the AND gate to check for 0. So that's why we use the lines 1, 1, because my input should be 1 in order to move with the TA branch. Once I move with my TA branch, I need to check for my jump instruction. So that's why it's 0, because I need to move on with the TA branch because it's satisfied. And then it goes through with the TA branch, and it ends up to the PC. So basically here, what's doing here, it's setting the 0 flag to 1. Are you guys okay with it?
Yeah, I'm looking at the AND gate kind of like a conditional, like it's like saying if we're branching and we have 0, then select TA branch.
Yeah. So because of my multiplexer is 0 or 1, so in order to move with the TA branch, my input that comes in should be 1.
Thank you.
So we only have 3 minutes left. Anthony, do you want to send in the group chat for the feedback? Or does anyone have any questions? So you need to, for the whole exam, you need to know the data paths, explain them. So once you know how to draw them, it's actually follow your lines, and that's how you explain it actually. Then try to memorize this, because she will ask you for one of them, like where it's used. So for the registered destination, it's used for the R format. So in your notes, I'm pretty sure you have this one, and these two. So it should be one of these 5, but I don't want to guarantee it. You need to know how to draw it. And then you find this from the table as well. The data path is given in your exam. It's the one that Joe sent in the group chat. Then one of the examples should be, one of the questions should be asking you to draw this, the data path, and explain it at the same time. And then you have the pipeline implementation to know for one thing. Let me,
Yeah, I was about to say, like is pipelining on your exam too?
yeah, it should be like,
Oh, yeah, I just realized I'm like, okay, because we didn't touch on that today.
I can go over it fast. It will take me 5 more minutes. So if, for example,
Okay.
I have add, shift left, add, store word, add I, and or. So from here, you can see that I have 1, 2, 3, 4, 5, 6 instructions. Briefly explain and draw a picture. So if I draw a picture of it, so what she's really asking you, let me, if I notice the picture that I have. So here is the add, shift left, add, store word, or all. So it goes from, because every single instruction you have, for the instructions, you have the if, ID, execution, and
Wait,
W.
memory, and then right back.
Uh,
And these five things that Georgios is writing, these correspond directly to the components in the data path. Like it's a correspondence. The IF, that's instruction fetch. The ID, and that's with the memory. ID is with instruction decode. with the register file. You have execution, which is the ALU. You have memory, which is just the main memory. And you have write back, which is
Right.
again um the register file.
So make sure,
Or
yeah,
yes, register file, right?
yeah.
Okay. Oh, but yeah, don't forget though, you have to put the memory between the execution and the write back. And yeah, we're good.
You have the one sec. Yeah, there is memory somewhere.
Yeah, yeah, exactly. It's between the EX and the WB.
Yeah,
Um,
man. So I start by writing my fetch. First I fetch. What's the ID? Do you remember?
yeah, so ID is instruction decode. And then um that's with that no instruction D. Yeah, yeah, exactly.
Yeah.
Mhm.
And basically what you need to do this whole time, so every instruction is 200, 400, 600, 800, 1000. So I will have the fetch. I need to decode the instruction. Then from my notes, I have the execution, and then I have the write back. But once it reaches the 200, because it's a pipeline implementation, I need to start my shift left, which is fetch again, ID, execution, and write back.
Oh,
I
you
do,
don't um so this is so with the you also have to factor into like all five stages, right? So we know that not all instructions may access all the components. So for example, the add, it doesn't access the memory component, but we would still have like all five stages for each instruction, like written here. If
so
that makes sense.
okay, so from what I see,
So like
you also
um
need the memory.
mhm,
Actually, you need the memory.
yeah.
And then it's write back. Text, mem, and write back. So it's a pipeline implementation. 1, 2, 3, 4, 5. Again, 1000, 1200, 1400. And right back for the store word. So it's the same. That's one of the given exercises, I would say.
Yes. And so when it comes to the pipeline questions, so this is like, pretty easy, but well, like straightforward, but she may throw something in that will make it not straightforward. Like for example, um, what's called a data dependency. So, I think I can draw on here too, Georgios. Like you can draw as well, but I think can you see what I'm drawing over here? Like this red scribble.
No.
You can't see
Oh,
that? You
yeah,
see
yeah,
it now? Okay,
yeah.
cool. So I'm just gonna make a comment over here. So he wrote just like the instruction, like what did like add or whatever. But you know, the full instruction, like as an example, let's say it was add, let's say, I don't know, S1 and then S2, S3, okay? S2, and then we have an S3. You know what? I'm just gonna type it. I think that's better.
So to finish this exercise before Anthony explains, we see that on the last instruction, the pipeline execution time will be 2000 because I'm done here, which is the 2000 PS. Yeah. So that's a pipeline implementation. It's not something very difficult, but Anthony, do you want to explain?
Yeah. So I'll add on. So this is a general pipelining case, and what Giorgio's drew is fine if we don't have any data dependencies. So this is like the ideal pipeline setup where uh, we have instructions sort of running in parallel. Okay, so while the add instruction is running over here, so it while it's in the second component in the decode stage, then we can start the shift left instruction in the fetch stage, and then this goes on, and then we do the next instruction. We start off, um, but meanwhile, like let's say we're over here, the initial add instruction is still working here, and now it's in the memory stage, while this add instruction is in the decode stage, so on and so forth. But sometimes we can't just stack it, simply like this. So over here, I typed, ooh, I can't drag what I had typed before. Can I modify this? I think I can modify it,
No,
but
you can't.
yeah, it won't let me select what I typed here. But in any case, well, right here, what I had typed with this add and sub and stuff, here we have an example of a data dependency. So from what I remember in class, right, we're going to be asked to, we have like a set of instructions like this, and we're asked to find the data dependency and draw that pipeline, like using forwarding or bubbles to resolve it. So the data dependency here is that oh, and yeah, Georgios has attached the feedback form. So we're supposed to end here at 3, but again, we didn't do the pipeline, and we want you guys to do well. So we're just spending some extra time on this. So make sure you fill that out as well. But in any case, the data dependency here is that essentially, remember with add, we take the last 2 registers and we put it in the first one over here, okay? But the next instruction is a sub, right? And the sub instruction is relying on this S1 register. So the problem here is that um I'm just going to draw like over here, right? How this would look. Um
Like, you,
yeah. Oh, thanks. Yeah. So let me just erase some of these lines or whatever. How do I do this? So let's say we have this specific add instruction, okay? And then we have this sub instruction. Okay. So we have our little boxes here like this. Okay. Bam, bam, bam. With the 5 components. But here is the problem. And yeah, these grid lines would just show us like the different stages. So um 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 so again, this is IF ID EX execution, and it's always in this particular order. Okay, there's no like switching it up. It's just this. And okay, there's other stuff I want to say too, but I'll just do this for now. And then again with the sub instruction here, you still have these stages, but it's just offset by 1. But the problem is that once we reach like the sub execution stage, the subtraction, which is going to be here, it's going to start executing over here. Um, what am I saying here? So basically the problem is we want to use the S1 register here when it's updated. Okay. But sometimes the register that we want to work with is not ready yet. Okay. So in this case here, we have this data dependency in which the S1 here may not be ready because we we put in the result in the S1 here in the add in the write back stage. Okay. We're writing back into this register. So here the S1 will be ready. But with the subtraction stage, we use the S1 here. You see that? So we can't do this, or rather, we're gonna have a problem here. So we can do a couple of things. We can do a bubble, or we can do forwarding. Let's show the bubble. So with the bubble here, um, can I just put in shapes? No, I can't. I can't. All right, whatever. It's fine. So this is how it would
You
look.
stop sharing.
Um, mhm.
I can stop
Oh,
sharing.
I can do shapes here. Let's do this. So that's 5. Okay. So we would do something like this where um I think this would work like this. Have this bubble here and it's still offset. So this would be 5 over here. And then we would have a bubble here. We could just denote it with like a little scribble, like um on like I like to just like draw a literal bubble over here. Okay. So then in this case here, um, what you call it? Or may do we I think we may need 2 bubbles actually, because here the S1 register is ready here and we're using it over here. Yeah, I think we need 2 bubbles. Let me modify this. And Georgios, if you have anything to comment, you can feel free to
Actually,
say something.
did the professor taught you that? Because it might be on the final instead of the midterm.
Oh, it might be on a final. Um, or how about you? So the people taking the test, did she go over the material that would be on the test and with like the pipelining and the hazards be on that test too? So making sure.
Let me check the bright space here.
Okay.
Pipelining should be included in midterm 2 material, yeah.
All right. So in this case here, yeah, let me do it like this. So it doesn't go, it's not fully on the screen here, but we don't need like all of the everything here. We just need to know when things are ready. So in this case, we're gonna have 2 bubbles. Okay. So why do we have 2 bubbles? So this is the execution stage for the subtraction instruction, and this is the write back for the add instruction. Okay. And you see when we have the bubble here, we offset it by 1 for each bubble we have. Okay. So that way now when so S1 should be ready here. And so now when we execute to do the subtraction, we have the updated value because S1's already computed. So we could do it like this. And so now we solve that data dependency. And so this is how the pipeline would look. Um, Alternatively, we can also use forwarding. And with forwarding, we still need a bubble, but I think in this case here we could just use just just one bubble here. So imagine we had one bubble, right? And then like this was like this rectangle would be over here or something, let's say. And then we could use like forwarding, or we just denote it with like a circle over here, and we would just connect it directly to the um execution stage. Or no. Sorry, we wouldn't do that. So actually, think of it like this. So with with the add, right? We're adding the S2, S3 and putting it to S1. So which will be over here. So in this case, in the execution stage here, we computed S2 plus S3. So we kind of have what's going to be in S1. Okay. It's not in S1 yet because we do it in the right back, but we have what's going to be in S1. So we can forward that result uh into the execution stage uh for the subtraction. Let me just make another rectangle here. So things maybe look a little messy here, but that's okay as long as you're following. So I'm gonna do this rectangle in a different color. Let's do blue here. Okay. So imagine we had one bubble. Okay. So it'll look like this. And so now the execution stage, let me do it like this. The execution stage for the subtraction will happen over here. And in this case now, we can forward. So with one bubble, we can forward and just go like this. Okay. So even though the result is not written in S1 yet, we have the answer still in the execution stage. So we forward it here. So that way, when we do the subtraction, we have the right value for S1. We subtract. And then we can go on from there. They just go on this way. So there's a couple of solutions to this one. You could do two bubbles, or we could do one bubble then forwarding. Does that make sense? And yeah, and Georgia, if anything else to say, feel free. But that's generally how we would address the pipelining, like the data dependency hazard we have here.
I think you explained it very well. And unfortunately, we don't have other time, but you are welcome to book an appointment for your exam and come to the Learning Commons, and we can help you more.
Exactly.
Yeah, because we haven't explained everything, but you are still welcome to come to the Learning Commons. Please make sure to fill out your feedback, our feedback form, so we know for the future what we can change or anything.
All right.
And
Thank you guys. Thank you very much.
Of
thank you.
course. All right, everybody. Have a great day.
All right. You too.
Take care.
Bye. Anthony, do you want to stop recording?